Hi, welcome back to Mr. Graham's Maths. Today we are doing a worked solution video for the Level 3 Calculus paper from 2024 for differentiation, and it's Achievement Standard 91578. Okay, so let's go with question number 1. We are differentiating this function here, and this is a little bit of chain rule, so I'm going to rewrite this in power form because that makes it easier to see the inside and the outside parts for me. So if we're doing chain rule on this, we differentiate the inside and times it by the derivative of the outside. So if we differentiate the inside, this bit just here, then we're going to get a minus 36x cubed times by the derivative of the outside, which is a half, and then reduce the power by 1 is minus a half here, and the inside remains the same. You can leave it like that if you wanted to simplify, then we'll half times the 36 will be an 18, and it will look like this. Okay, next we have, we're going to find the gradient of the tangent to this curve, which means we need to differentiate and then sub in the value of x equals 0. So dy by dx on this function, we've got a product rule, we've got one thing times by another thing. So that means that we differentiate the first and times it by the second, and then differentiate the second and times it by the first. I will actually write this out in full for anybody that struggles to see this. So x squared plus 3x plus 2, and v is sine x. Remember, you've got product rule on your formula sheet. So du by dx is 2x plus 3, and dv by dx, you've got the derivatives of the trig function on your formula sheet. If you differentiate sine, you get cos x. dy by dx then is u times dv by dx, so cos x, x squared plus 3x plus 2, plus v times du by dx, so sine x, 2x plus 3. And then you just need to check that you have answered the question, which is to find the gradient of the tangent when x equals 0. So when x equals 0, dy by dx is, now if we go over to our calculator, let's try cos 0 first is 1, but sine 0 is 0. So we actually only need to do the first bit. So it would be cos of 0, for when I'm talking about this first bit, let me just find my cursor. It's this bit just here, because if we do this bit, the sine x is going to be a 0, so that's going to fall away. So popping in x equals 0 into here means this bit is equal to 1, 0 squared is 0, 3 times 0 is 0, and then plus 2. So it'd be 2 times 1. So our gradient is 2. Okay, for a decreasing function on part C, so decreasing is when dy by dx is negative, less than 0. So the gradient is going down. Okay, so if we differentiate these pieces one at a time, so we've got a little bit of chain rule here, that'll be, let's do it in parts. So 3 times the 2, so differentiating the outside, and then times it by the derivative of the inside. Now, you may have done that all at once, in which case it would then simplify to this. And then the derivative of log x is 1 over x, so this will be 60 over x, and then if you differentiate 12, you get 0. Now we want to know, when is that less than 0? So multiplying that bracket through, we've got 24x minus 12 times 7 is 84, plus 60 over x has got to be less than 0. Now this is actually a quadratic in disguise. If we multiply everything through by x, we get 24x squared minus 84x plus 60 is less than 0. Now we can divide everything through. The highest factor there, I think, is going to be 12. So if we divide everything through by 12, we've got 2x squared and then a minus 7x and a 5, like so. This one factorizes into 2x and x, and then that's going to be a minus 5 and a minus 1. Now think about your critical values for working out when that's below 0. So this is a positive parabola. It's going to go through 2 points here, and we want to know when it goes below 0 like this. So the first value that we've got, well, our x values for the solutions from these two factorized brackets is 5 over 2 and 1. So that's 2.5 and 1. So this will be the 1, this will be the 2.5. So for when that parabola goes below the 0 line, that will happen in between those two values. So x needs to be between 1 and 2.5. For part D, we're finding stationary points and then also working out what type of stationary point we have. So to find a stationary point, we want dy by dx equals to 0. Okay, dy by dx, on this we're going to do the product rule. So we've got u stays as it is, times by the derivative of the second part, which is going to be minus 2e to the minus 2x, plus the derivative of the first times by the second part unchanged, like this. And we want to set that equal to 0. Okay, now we can take out a factor of e to the minus 2x. In fact, we can take out 2e to the minus 2x. We'll be left with minus 2x minus 1, and then a plus 1. Now the reason that we do that is because whenever we've got this e function, we're looking to pull that out as a factor because e cannot be equal to 0. So it leaves us with this part in the bracket must be the bit that equals 0 if we're timesing two things together to make 0. So can't be 0, therefore minus 2x plus 1 plus 1, so that'll be plus 2, has to equal 0. So 2x equals 2, x is 1. Okay, so we've got a stationary point when x equals 1. Now we need to know what kind of stationary point it is. So we find the second derivative. Before I do, I'm actually going to rewrite the dy by dx, but in simplified form to make that a bit easier. So we had the 2e to the minus 2x, and then a bracket minus 2x plus 2. Actually, we can take out another factor of 2 from that bracket, so I'm going to leave that as a x plus 1 and turn that into a 4. Okay, now if we are differentiating this again, we're going to have the first term, leave it as it is, times by the derivative of the second term, which is minus 1, and then differentiate the first term, we get minus 8x to the minus 2x times by the second term as it is. So when x is 1, the second derivative is going to be, we'll go over to our calculator, so 4e to the, so if x is 1, it's going to be a minus 2 times by minus 1, and then let's add on minus 8 times, we've got 1 to the power of minus 2, so 1 to the power of minus 2, and then it gets multiplied by minus 1 plus 1, it's 0. Okay, so we actually are going to end up with that second term being equal to 0. So in the end, we have minus 0.541. This is less than 0. Therefore, there's a maximum at x equals 1. Okay, part E. We've got this equation here. We've got a point of inflection at point P. We must find the equation of the tangent to the curve at point P. Now, a point of inflection happens when the second derivative is equal to 0. So I'm going to start by simplifying this equation, dividing everything through by x. So we have 2x minus 1 over x minus 2 natural log of x. Now, first derivative, we can do each of those terms. Rewrite this 1 over x as x to the minus 1, makes it a little easier to see. Now if we differentiate that, we get plus x to the minus 2, and then natural log differentiates into 1 over x. And that one actually I'm going to rewrite as 2x to the minus 1 because I know I've got to differentiate it again. So the second derivative now is going to be minus 2x to the minus 3 plus 2x to the minus 2. Now, a point of inflection happens when this is equal to 0. This is going to be easier for me to see if I rewrite these as fractions. So this is 2 over x squared. Okay, so now 2 over x squared is equal to minus 2 over x cubed. So 2x cubed is equal to, oh wait, sorry, not a minus, it's a plus because I moved it over to the right hand side, 2x squared. Now at this point in these questions, you've got to be careful not to just divide through by x's, but rather factorize instead, because it's possible to lose solutions if you just divide through by x. So let's bring these back over to the same side, and then we can factorize. So if we take out 2x squared, we get x minus 1, like this. Okay, now let's work out what could happen. So either 2x squared equals 0, or x minus 1 equals 0. Well, this one is not valid because in our question it said that x has to be greater than 0. That would give us x equals 0. So x equals 1. Okay, now find the equation of the tangent to the curve at that point. So P is at the point where x is 1, and our y value, we can pop it back into this bit just here. So we'll have 2 minus 1 over 1, which is just 1. So we're up to 1, and then minus 2 log 1. Well, log of 1 is 0. So we've got, where's my cursor? There we go. 2 minus 1 minus 0 is going to be 1. Then we can find the gradient at P. So when x is 1, use this gradient equation here, we'll get 2 plus 1 minus 2. So the gradient is 1. Then we use y minus y1 equals m x minus x1. So here's our x and y points, here's the gradient, sub that in. And simplifying, we get y equals x as the gradient of that tangent. On to question 2 now. Okay, we've got a parametric set of equations, and we need to differentiate to find dy by dx. So we start with dx by dt, differentiating each one, and dy by dt is minus sine t, and then dy by dx is to do dy by dt times dt by dx, which means we're going to take minus sine t and then multiply it by dx by dt flipped over, because it's dt by dx is what we want, so 1 over 6t. You can simplify that to be minus sine t over 6t. We've got a kinematics question for part B. We've got the displacement formula given as s of t. We want to find the velocity. So the velocity is if we do the derivative of the displacement. We're differentiating a log function, which means we differentiate the inside and put it on the top. So that'll be 6t plus 5, and the original of the inside goes on the bottom. That's how we differentiate log functions. Okay, now when t is 1, we're going to sub in 1 into this. So it'll be 6 plus 5 over 3 plus 5 plus 2. So that's going to be 11 divided by 10. So 1.1. And our units in this one is we're measuring in meters per second. You can just put 1.1 though as your final answer. You don't need the units for this achieved question. Okay, part C, we want to show that this equation works when y equals sine of x squared minus cos of x squared. So we need the second derivative for this part here. So we'll have to work through the first derivative. Now for the sine of x squared, I'm just going to do it over here. This is a chain rule, and sometimes they are a little bit harder to see with trig functions, so I'll just write it out in here. Du by dx would be 2x, and dy by du, sine turns into cos u, so timesing them together gives us our answer, so it'll be 2x cos u, which is x squared. So the derivative of that first term is 2x cos of x squared, and the second term, this minus cos x, well, cos goes to minus sine, so that becomes a plus sine x. Now the second derivative, we're going to do, this time we've got a product rule with 2x times by the cos x squared. So again, let me just do that over at the side to keep track of things well. So if we're doing 2x cos of x squared, u is 2x, v is cos of x squared, which that one we're going to have to do a chain rule on it like we did with the one above with sine x squared. So du by dx is 2. dv by dx, we follow the same logic that we had up here. In fact, I'll rewrite it and you can see as I go. So if this was a cos here, this would be a cos, and that would turn into a sine. Is it -1? Quick little check on the formula sheets. That's a minus sign there. So then this will just here be turn that into a negative. So this one becomes a minus 2x sine of x squared. If I could squeeze that in a little bit. And put them back together for dy by dx using the product rule. So that'll be 2x times dv by dx here. So actually, let's move this over a little. dy by dx. So that's going to be minus 4x sine of x squared, and then these two times together. So plus 2 cos of x squared. Okay, let's pop that back into what we were doing over on the left. So we've got minus 4x sine of x squared plus 2 cos of x squared, and then the sine x turns into a plus cos x. And just, I'm actually going to delete those side scribblings out the way so we're not getting confused with tons of stuff that I was showing you. Okay. Now we need to show that this will be true. So if we start with d2y over dx squared plus 4x squared y, so that's now going to be minus 4x sine of x squared plus 2 cos x squared plus cos x plus 4x squared times y. Now y was sine of x squared minus cos x. Okay, so we've got, working through that, I'm going to expand that bracket. I've just got to write a whole bunch of stuff first for that first bit. Okay, then plus 4x squared sine of x squared minus 4x squared cos x. Okay. I missed a little negative here just at the start. That should have been a minus. Okay, now that's important because this one now cancels with this one. And then we're left with 2 cos of x squared, which is good because that's the first bit just up here that we wanted. Now, using this as a clue, for the rest of it, let's take a factor of cos x out of these parts that are left. So plus cos x would leave us with a 1 from this bit and a minus 4x squared from this bit, which is the right-hand side that we wanted up here. Right, for part D, we want to find the point of inflection, and that happens when the second derivative is equal to 0. Now, we've got a quotient rule happening here, where u is natural log of x, v is x. So du by dx is 1 over x, dv by dx is 1, and remember you've got quotient rule on your formula sheet. So the first derivative of f of x is v du by dx, so x times 1 over x is 1, minus u dv by dx, which is going to be log of x, all over v squared, which is x squared. Now we've got to find the derivative of that for the second derivative, so we've got another quotient rule. This time u is 1 minus natural log of x, v is x squared. So du by dx is minus 1 over x, and dv by dx is 2x. So the second derivative is to do v du by dx, so x squared over x minus 1 over x is going to be minus x. Then minus u dv by dx, so that's 2x 1 minus log of x, all over v squared, which is x to the 4. So if we can tidy that up a bit, because we need to use it for some other stuff. So this will be multiplying out that bracket, looks like this, all over x to the 4. Well, the minus x minus 2x becomes a minus 3x, and we can cancel through by an x. So that'll be minus 3 plus 2 log x over x cubed. Okay, now point of inflection happens when that is equal to 0. So if we bring the x cubed up and times it, that's going to become 0. So minus 3 plus 2 log x equals 0. So 2 log x is equal to 3. Log of x is equal to 1.5, or 3 over 2. So x equals e to the 1.5. Okay, now we want to find the coordinates of the point. So we've got the x coordinate, now we need the y coordinate. So y is equal to log of x over x. So log of x, which is e to the 1.5, over e to the 1.5. The e and the log cancel, so that's just 1.5 divided by e to the 1.5. Let me just pop this into here. Where's my e gone? E to the 1.5. So that's going to be 0.335, while x is 4.48. So there we've got our x and y coordinates. Let me just tidy that zero up a little. There we go. Okay, part E. We're told that this function here has just one turning point on its graph. We want to find out where that is. So turning points happen when the derivative is equal to 0. So we're going to need to differentiate this function. So let's set u is equal to x e to the 3x, v is equal to 2x plus k, and we're using quotient rule. So du by dx, this one actually has a product rule inside of it. We've got the x times e to the 3x. So differentiate the first term is 1 and times e to the 3x, just leaves us with e to the 3x, plus leave the first term as it is and times by the derivative of the second. Okay, so then dv by dx is equal to 2. Remember, k is just a constant. We're told that in the question up here. So when we differentiate, that differentiates to 0. So then dy by dx, I'm going to just tidy up this du by dx first. We have e to the 3x plus 3x e to the 3x here. Using quotient rule is v times du by dx first, so 2x plus k times e to the 3x plus 3x e to the 3x minus u times dv by dx, so 2x e to the 3x all over v squared. Now, turning points happen when this is equal to 0. And we're going to need to solve this. Now, if I start solving, I'd bring this up to here and make it equal to 0. So we're only actually interested in the numerator of this equation. So we've got 2x plus k. Then e to the 3x plus 3x e to the 3x minus 2x e to the 3x equals 0. Now, you might remember earlier I talked about when we've got e to the something in these things, we try to factorize it out because we know that can't equal 0. So if I take out e to the 3x as a factor of this first one, we get 2x plus k is what it's all going to be times by. And then this bit would be multiplied by 1 plus 3x. I can take out an e to the 3x of this one as well, and it's 2x. So this is e to the 3x of 2x plus k, 1 plus 3x minus 2x equals 0. We do that because this can't be equal to 0. So then we're left with 2x plus k, 1 plus 3x minus 2x must be equal to 0. Now expanding those brackets out, we get 2x plus 6x squared plus k plus 3kx minus 2x is 0. So that's 6x squared. This 2x cancels with that one, so we're left with 3kx plus k equals 0. Now with this quadratic, it's tempting to want to dive straight into solving it. but we need to work out what k can be first, and you were given a clue to doing that by being told this bit here, it has a single turning point. So remembering down here that what we're trying to do is find where that turning point is. We set this equal to 0 to do that, and if there's only one turning point, there can only be one solution to this equation here, which means that the discriminant would be equal to 0. So b is 3k. I'm going to square that, minus 4 times 6 times k, which is c, and set that equal to 0. So 9k squared minus 36k equals 0. So taking out a factor of 9k, we get k minus, that was silly, 4 times 6 is not 36, 4 times 6 is 24. Okay, so now taking out a factor of 3k, we can get 3k minus 8 here. Now what were we told about k up here? Here we go, that's what I was looking for. K is a non-zero constant. K can't be 0. Okay, so this would give us k equals 0 from the 3k, not valid. Okay, so we ignore that, and we're going with the 3k minus 8 equals 0, so k equals 8 over 3. We're going to take that and pop it back into our quadratic here so that we can solve it. So using this quadratic now with the value of k put into it, we will have 6x squared plus, like 3 times 8 over 3 is going to be 8, so that'll just be 8x plus k is 8 over 3, and set that equal to 0. Now we could do quadratic formula or equation solver or whatever to find the answer to this. Let's work it through. I'm going to multiply everything through by 3 to get rid of that 3 on the bottom there. And then this can also be halved, so 9x squared plus 12x plus 4 is 0. Let's try factorizing it. That feels like this will go into 3x and 3x, and a 2 and a 2. And yes, that works. So we've got 3x plus 2 as our repeated root, so x is equal to minus 2 over 3. We'll just pop that all onto the one screen for you to see there. That was lengthy. Okay, on to question 3. Okay, we're going to differentiate this. We've got a product rule. U is x to the half, and v is sec of 6x. du by dx is half x to the minus half, and use your formula sheet for sec. Now sec goes to sec tan, so it'll be sec 6x tan 6x, but because we have the 6 on the inside, it's also a chain rule, so it gets times by the 6. So dy by dx will be u times dv by dx, so x to the half times by 6 sec 6x tan 6x, plus v times du by dx, so half x to the minus a half times sec of 6x, and it tells us we don't need to simplify, so I'm not going to. Okay, part B. For this function, we need to find the values of x where f of x is continuous but not differentiable. So that means that you're not continuous means we can draw it without taking our pen off the paper, but not differentiable means it's not a smooth point. So we're looking for kinks in the graph, and that's happening just here. So that's when x equals 5. For the next bit, we want to find the values of x where the derivative is equal to 0. So equal to 0 happens at turning points or when the graph is horizontal, flat. So turning point is just here at x equals 1. And then the graph is flat between 3 and 5. And we're going to go with a strictly less than, not, or equal to, because we actually can't differentiate it at 3 and we can't differentiate it at 5. So it's got to be between those two, not equal to them. Now, what's the limit as x approaches -1? So let's look at -1, and we want to say as we're coming towards -1 from both sides, what are we getting towards? We're approaching 1. Okay, done. Okay, part C, we're finding the stationary points of this graph, which means we need to differentiate it and set it equal to 0. So first of all, I'm going to do quotient rule on this. So differentiate u, we get 2x minus 5. Differentiate v, we get 2x plus 5. So the quotient, the quotient rule says we're going to do v du by dx. Oh, I'm going to need more room. Let me pop it down here. Okay, so v times du by dx, this one, is going to be 2x minus 5 times x squared plus 5x plus 4 minus v u dv by dx. So this one, 2x plus 5 times by x squared minus 5x plus 4 all over v squared, which is x squared plus 5x plus 4 all squared. All right, now let's simplify. Actually, before I do, I'm going to set that equal to 0 first so that we can not have to keep writing out the denominator of this fraction, because when we bring this up, it's going to times by 0. So then multiplying out through the top, okay, we're going to have 2x cubed minus 2x times 5x is 10, x squared, 8x, minus 5x squared, plus, nope, minus 25x minus 20. Just move that over a little bit because we've got a lot to do here. And then the second set of terms, we're going to have minus 2x cubed plus 10x squared. So I'm up to this bit, so minus 2x timesing by that one. We got minus 2x times the 4 is minus 8x. And then we'll take the minus 5 times all of that, so minus 5x squared plus 25x minus 20. That all has to equal 0. Okay, let's do some cancelling. That one cancels with that one. That one cancels with that one. That one with that one. Then we've got this one with this one. Okay, so minus 10x squared is left, and so is 40. We'll equal that to 0. So 10x squared equals 40. X squared equals 4. So x is plus or minus 2. And I wish I could see an easier way to spot it than doing all of that expansion. Let's just check we've answered the question. Find the x values of the stationary points. Yes, we've done that. We don't need to find y values for this one. Now, on the digital copies of these papers, there's often redacted photos, but I did take a scan of this paper. So there's the picture for you. Not important to the question, but just in case you were wondering what was there. Okay, this one is a rates of change question. We've got some flour being added into this conical pile of flour. Now, the way that I do rates of change question is to read through and write down the information in rates versions as much as possible. So the first here is the flour is being added at a constant rate of 3 centimeters per second. So the rate of change of the volume of flour over time is 3. We want to find the rate that the height is increasing. So we will need to find dH by dt. And that gives us some clues that we need to link volume and height. And so we're using the volume is being equal to 1/3 pi r squared h. Okay, so we've got quite a bit of information so far. We do need to find something that links together the radius and the height, though, because we can't currently differentiate v when it's got two variables in it. So looking at our cone, we've got r and h that was marked here and here. Okay, oops, and we're also told that this bit here, the height of the pile, is always the same as the diameter of the base of the cone. So the radius will be half as much as the height because the diameter was the same as the height. Now we could either express h in terms of r or r in terms of h. I've chosen to keep things in h's because I know that it's dh by dt that I want at the end of this, so I need things in h's. Okay, so if we then adjust our volume formula, r squared is h over 2 squared, and that's going to times by h. So if we multiply that out, the half squared is 1/4, and times that by the third, we've got a 1/12, and then the h squared times h is h cubed. Okay, now we can differentiate dv with respect to h, so dv by dh, taking this formula and differentiating it. Bring the 3 down is 3 over 12, which cancels to 1/4 pi by h, and then reduce the power of h by 1, so 1/4 pi h squared. To find dh by dt, start with the thing we know, dv by dt, and what do we need to times that by? We need to introduce dh on the top, and we need to cancel out dv on the bottom. So that's what we had here, but flipped over. So dv by dt is 3. If we flip over dh by dv, we've got, well, let me write this like this, it might be easier to see. Flip that over, and we've got 4 over pi h squared. So that's 12 over pi h squared. Now we want to work out what that is when the pile is 4 centimeters high. So when h equals 4, dh by dt is 12 over pi times 4 squared. Oops, hang on. Oh goodness. 12 divided by 16 pi, 0.2387 or 0.239. We're measuring that in centimeters and seconds, so it'll be centimeters per second, although the units aren't required for you to get the mark here. Okay, last part. Okay, we've got this diagram with this function here. Now, when we place the point P on this curve, we set a point Q so that OP and OQ are the same length. And then we want to work out what's the largest possible triangle that we could make like that and prove that it's equal to this. So first of all, we need to come up with a formula for the area of the triangle, and then we will use differentiation to maximize that possible area. So we need to come up with a formula for that area of the triangle, which will be half the base times the height. Now P is at an x-coordinate of x, and the y-coordinate is going to be the value of the function there, e to the minus x squared. So P is at x, e to the minus x squared. Okay, so now thinking about the area, half times the base. Well, if this distance here is x, then the whole base from here to here is twice that much because this was symmetrical, right? It's an isosceles triangle. So the base will be 2 times the x-coordinate, and the height, well, the height here is just the value of y at that point, which is e to the minus x squared. So times e to the minus x squared. So that simplifies to being x e to the minus x squared. So let's pop that down here. Area is x e to the minus x squared. Now, if we want to maximize a function, we need to differentiate it and set it equal to 0. So let's differentiate this. It's a product rule. So u equals x, v equals e to the minus x squared. Du by dx would be 1, and dv by dx is a chain rule, so it's minus 2x e to the minus x squared. Okay, so product rule says we're going to do u times dv by dx minus v times du by dx. So we will have minus 2x squared e to the minus x squared plus e to the minus x squared. Just erase that so we can use that space, because now we're going to set that equal to 0 to find the maximum. Let's take out a factor of the e portion like I've shown you before. We'll have minus 2x squared plus 1 is equal to 0. This bit here can't be 0. So therefore minus 2x squared plus 1 equals 0. So 2x squared equals 1. X squared is a half. So x is plus or minus 1 over root 2. Okay, now thinking back to the question again, we're finding this area. X is here on the positive axis, so therefore x must be the positive one of those solutions. So x is 1 over root 2. And finally, we actually need to find the area itself. So prove the largest possible area is this much. So now let's put that into our area equation. So when this is true, area is equal to x e to the minus x squared. So that's 1 over root 2 e to the minus x squared. So that's this one squared, which actually we have over here already. So it's e to the minus a half. Now, something to the power of a half is a square root, and making it a negative one means it's on the bottom. So that's 1 over the square root of e, which equals 1 over the square root of 2e. We can combine those, and then we've got what we needed as required.